Jeremiah the Geometry Cowboy talking to you about two-dimensional figures. What did the cow say to its calf when it was being bullied? You gotta turn the other cheek.
First thing we're going to talk about is a polygon. That's a closed figure formed by a finite number of coplanar segments called sides, such that the sides have a common endpoint and are non-collinear, and each side intersects exactly two other sides, but only at their endpoints. Now let's break this down. A polygon is a closed figure, meaning there can be no openings. So here you can see that this is completely enclosed, completely enclosed, completely enclosed. Therefore, each of these would be considered a closed figure. And it's formed by a finite number of coplanar segments. Finite number just means it's not an infinite number of sides, which would eventually create a circle, and we'll show you that later on. And a number of coplanar segments just means each of these segments has to lie on the same plane, which they do because this is a two-dimensional figure. These sides have a common endpoint and are non-collinear. So these two sides are not on the same line, they're non-collinear, and they have a common endpoint. Over here, these two sides do not lie on the same line, but they do have a common endpoint. And each side intersects exactly two other sides. So let's look at this figure. This side right here intersects this side and this side at each of these points. This side right here intersects this side and this side at each of these points. This side right here intersects this side at this point and this side at this point. Over here, this side right here intersects this side at this point and this side at this point. So that's how you can see each side intersects exactly two other sides, but only at their endpoints. Now we've looked at what are polygons, so it might be helpful to see what is not a polygon. So here you can see this is not a closed figure, right? There's an opening right here. Because it's not a closed figure, it cannot be considered a polygon. This figure as a whole would not be considered a polygon because two of the sides do not just intersect at the endpoints. They intersect right in the middle of the side. But technically you could consider this by itself and this by itself a polygon. Here, this is a closed figure, yes, but remember, it has to be a closed figure made up of a finite number of coplanar segments. Segments would be line segments. This wavy curve would not be considered a line segment. Therefore, it cannot be considered a polygon. The next vocabulary term is a concave polygon. So there's two types of polygons. The first one is concave, and that's a polygon with one or more interior angles greater than 180 degrees, also called a reflex angle. It sort of looks like a vertex has been pushed in towards the interior of a polygon. So here you can see we have three different polygons, and these are all polygons. However, one of the angles is a reflex angle, meaning that its measure is greater than 180 degrees. So here we have a reflex angle greater than 180 degrees. Here, a reflex angle greater than 180 degrees. Here we have a reflex angle greater than 180 degrees. Because each of these polygons has an angle with a measure greater than 180 degrees, it would be considered a concave polygon. And an easy way to remember that is it looks like it's being caved in, caved in, caved in. Now on the flip side of that, we have a convex polygon, and that's a polygon with all its interior angles less than 180 degrees. So here you can see we have three different polygons, and each of the angles in each of these polygons are all popped out. None of them are popped in or caved in. You can see they're all extended outward, and they all measure less than 180 degrees. There are no reflex angles in any of these polygons. Therefore, they're convex polygons. Now the next thing we're going to talk about is the equilateral polygon. That's a polygon in which all sides are congruent. So equa means equal, lateral is talking about the sides. So equilateral means equal sides. So we're looking for polygons with congruent sides. Here you can see that all of these sides in each of these polygons are congruent. This polygon right here is an equilateral hexagon because all the side lengths are congruent. And you know that because each has the same amount of tick marks. Over here, we know this is an equilateral pentagon because all the sides are congruent. And we know that because they all have the same amount of tick marks. We have an equilateral rhombus, same thing. The same amount of tick marks on each side lets you know that each side is congruent to the other. Now, you will either be given tick marks or you'll be given the actual measures of each side, like 5 centimeters, 5 centimeters, 5 centimeters, 5 centimeters. That will still tell you that it's an equilateral polygon. Now, an equiangular polygon is a polygon in which all the angles are congruent. Remember, equa means equal, angular is obviously referring to the angles. So here you can see three different equiangular polygons. And equiangular, you can usually tell a polygon is equiangular because each of the angles has the same amount of arcs. So here, each one has one arc, meaning that we know all the angles are congruent. It also has the same measure. So that's another way to tell if it's equiangular. Here we have a square. And again, a square or a rectangle is likely going to have these little red boxes in the corner. And if each corner has a little red box, that just means each angle measures 90 degrees, which means it's equiangular. Now, a regular polygon would be a polygon that is both equilateral and equiangular. So here we have 3 different polygons that are both equilateral and equiangular. This is an equilateral triangle, and we know it's equilateral because each side has the same amount of tick marks. We know it's equiangular because each angle has the same amount of arcs. So it would be considered a regular triangle. Here, this would be a regular quadrilateral because each side has the same amount of tick marks and each angle is 90 degrees, meaning that it's both equilateral and equiangular. Here we have a 1, 2, 3, 4, 5-sided figure that we're going to talk about later on. And we know that each side is the same measure. That's what the tick marks mean. And each angle is the same measure. That's what the arc means. Therefore, it's a regular polygon. Now, perimeter is going to be the sum of the lengths of the sides of a polygon. So here we have a polygon, and we know the measures of each side. So if we want to find the perimeter of this polygon, all we have to do is add the measures of each side, or the lengths of each side together, and we get the perimeter of that given polygon. Now let's talk about the anatomy of a polygon. So here we have a polygon. It's completely closed. And each of these red segments would be considered a side of the polygon. Then we look at each of these hinges where the angles form. These would be considered, if you thought about an angle meets at a vertex. So each of these then would be considered a vertex. We have a vertex here, vertex here, vertex here, vertex here, and a vertex here. We also know that outside of our polygon, this would be considered the exterior of your polygon, and then inside would be considered the interior of your polygon, just so you know. Now let's quickly go over the names of polygons. So a 3-sided polygon would be considered a triangle. A 4-sided polygon would be considered a quadrilateral. A 5-sided polygon would be considered a pentagon. A 6-sided polygon would be considered a hexagon. A 7-sided polygon would be considered a heptagon. An 8-sided polygon would be considered an octagon. A 9-sided polygon would be considered a nonagon. A 10-sided polygon would be considered a decagon. An 11-sided polygon would be considered a hendecagon. A 12-sided polygon would be considered a dodecagon, and anything above 12 would be considered an n-gon. So if it had 13 sides, it would be considered a 13-gon. If it had 20 sides, it would be considered a 20-gon. Okay, that's how you name anything above 12. And quickly, I'd like you to note that as a polygon gets more sides, what does it start looking like? Starts looking like a circle, right? So actually, a polygon with an infinite number of sides actually becomes a circle, and that's something to remember later on.
Now you got the vocab. It's example time.
Now, example 1 says name each polygon by its number of sides. Classify it as concave or convex and regular or irregular. So the first thing we're going to do here, we're going to name each polygon by its number of sides. So let's name this polygon by its number of sides. So we'll start with this side. We have 1, 2, 3, 4, 5, 6, 7 sides. So a 7-sided polygon would be considered a heptagon. Then we're going to classify it as concave or convex. So is it concave or convex? Are there any reflex angles in this polygon? Yeah, there is one interior angle that is greater than 180 degrees. Because of that, this would be considered a concave polygon. It looks like one of the angles has been caved in. Next, is it regular or irregular? Well, remember, a regular polygon just means all the sides and all of the angles are congruent. Does it look like all the sides are congruent? There's nothing that gives you that indication, and not all of the interior angles are congruent. There's nothing that says that. Therefore, you would say that this is a concave, irregular heptagon. Part B, we have this 4-sided figure right here. Since it has 4 sides, we already know it's going to be considered a quadrilateral. Next, is it concave or convex? Are there any reflex angles? Do any of the angles cave in? No. Because there's no reflex angles, all of the angles look like they are 90 degrees, which is less than 180. We know it is a convex polygon. Now, is it regular or irregular? Again, regular just means it's equilateral and equiangular. Does it look equilateral? Yeah, each of the sides are congruent. That's why each of them has 1 tick mark. Is it equiangular? Yeah, each angle measures 90 degrees. That's why they all have these little boxes in the corner. Therefore, it's both equilateral and equiangular, meaning it's regular. So this would be a convex, regular, quadrilateral, or you know it better as a square. Now part C, again, we want to name each polygon by its number of sides. So how many sides do we have here? Well, starting with this side, we have 1, 2, 3, 4, 5 sides, which would be a pentagon. We then classify it as concave or convex. So are there any reflex angles here? Yeah, this angle right here measures greater than 180 degrees. Therefore, it's a reflex angle. Therefore, this is a concave polygon because it looks like one of the angles has caved in. And then is it regular or irregular? Well, again, regular just means it's equilateral and equiangular. All the sides are congruent and all the interior angles are congruent. Well, does it look like all the sides are congruent? There's nothing that says that, so no. Does it look like all the interior angles are congruent? No, it does not. We have a reflex angle, so obviously this is not a regular polygon. It's irregular. So this would be a concave, irregular pentagon. Part D, we have this one right here. First, we're going to name it by its number of sides. So starting with this side, we have 1, 2, 3, 4, 5, 6 sides. That would be a hexagon. Then we're going to classify it as concave or convex. So is this a concave or convex polygon? Well, it doesn't have any reflex angles like over here. There's no interior angle measuring greater than 180 degrees. Most of these are between 0 and 180 degrees. So we can consider this a convex polygon. Then is it regular or irregular? Well, regular means all the sides are congruent and all the angles are congruent. It's equilateral and equiangular. Does this look equilateral and equiangular? Yes, it does. But is there any way you can prove it? Is there any way that the figure shows you that it's equilateral and equiangular? No, there's no tick marks and there's no angle measures. So we can't say for certain that this is a regular polygon. So we're going to say that this is a convex, irregular hexagon.
Saddle up, partner. Time for a new try.
Okay, doing the same thing here. So first, we want to name each polygon by its number of sides. We'll start with this side right here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. So that would be considered a decagon. Next, is it concave or convex? Does it have any reflex angles, any interior angles measuring greater than 180 degrees? No. All of these look like they're between 0 and 180 degrees. So therefore, this would be considered a convex polygon. Next, is it regular or irregular? Well, regular means it's equilateral and equiangular. So do all the sides look congruent? Yeah, they all have one of these green tick marks. Do all the angles look congruent? Yeah, they each have a red arc, meaning that this is a convex, regular decagon. Here, we have a three-sided figure, which we know is a triangle by now. This would technically just be considered an isosceles triangle. Next, is it concave or convex? Well, each angle points outward and is less than 180 degrees, meaning that it would be considered a convex polygon. And then is it regular or irregular? Well, it looks like it could be regular, but we don't have enough information, right? We would need one of these tick marks to be on this side, and we would need to know what each angle measure is, or to know that each angle is congruent. So this would be a convex, irregular triangle. Now example 2 says find the perimeter of the following polygons. So here we are finding the perimeter of a 1, 2, 3, 4-sided figure. That's a quadrilateral. So perimeter just means we want to find the sum of the lengths of each side. So the sum of the lengths of each side, just add together the measure of each side length. So what's 1.3 meters plus 1.2 meters plus 2.7 meters plus 2.4 meters? That's 7.6 meters. So that's our perimeter of this quadrilateral. Part B, we are finding the perimeter of a 1, 2, 3, 4, 5, 6, 7, 8-sided polygon, which would be considered an octagon. So to find the perimeter of this octagon, we just have to add together the measure of each side length. Well, we are missing a side length here. How do we find this? Well, we know that this entire side is 9 centimeters. And then up here, we have a 4 centimeter portion and a 3 centimeter portion. If we're to believe this side length is the same as this side length up here, then all of these 3 side lengths would have to add together to equal 9 centimeters. So 4 centimeters plus 3 centimeters is 7 centimeters. We would need another 2 centimeters in order to get the full 9. That's the same as this side. Okay, now we have the length of each side. Now we can find the perimeter of this given polygon. So to find the perimeter of this octagon, we add together the measures of each of the side lengths and we end up getting a perimeter of 34 centimeters.
Don't just sit in a barrel like a rodeo clown. You try.
Okay, so part A says we're going to find the perimeter of a regular hexagon with a side length of 2 1/3 inches. Well, it only gives us one side length. How in the world do we do this? Well, a regular hexagon means it's both equiangular and equilateral, meaning that all the sides are congruent. So if all the sides are congruent, that means each of the 6 sides in our hexagon is going to measure 2 1/3 inches. So if one of the side lengths is 2 1/3 inches and they're all congruent, then each side length is 2 1/3 inches. So really, all we have to do to get the perimeter is add up each of the side lengths. Well, since there's 6 side lengths and they're all the same, why don't we just take one of the side lengths and multiply it by 6? That'll still get us the same perimeter. So how do I multiply 6 and 2 1/3? Well, 2 1/3 I need to put as an improper fraction. So 2 1/3 is the same as 2 times 3, which is 6, plus 1, which is 7. So that's the same as 7/3 inches, which I can then now multiply the 6 and the 7/3, because 6 is the same as 6 over 1. So I multiply the numerators together and denominators together. What's 6 times 7? That's 42. And 1 times 3 is 3. So I get 42 over 3 inches. Now, how does this simplify? Well, 3 goes into 42 14 times. So we get 14 inches as our simplified final perimeter. Now in part B, doing the same thing. We want to find the perimeter of this 1, 2, 3, 4, 5, 6, 7, 8-sided polygon, which we call an octagon. But in order to do that, we need all the side lengths. We are currently missing 1, 2, 3 side lengths. So let's find those. This one we can assume is the same as this side length over here. So this would be considered 8 meters. This side length right here, we can assume is the same as this side length right here, so that would be considered 2 meters. This one would probably be the hardest. We know this full side length is 14 meters, and we know this plus this should equal 14. And if we already know that this plus this is 10 meters, that leaves 4 meters for this segment right here. Now that we have all the side lengths, we need to add them together in this polygon in order to get our perimeter, which is 48 meters. Now example 3 says graph the figure with the given vertices and identify the figure. Then find the perimeter of the figure. So we have 3 points, point R, point S, and point T. So point R is at -3, -3. So we put a point there. Point S is at 5, -3, so we go over to 5 on the x-axis down to -3 on the y-axis, put a point. And then point T is at -3, +3, so over to -3 on the x-axis up to +3 on the y-axis, put a point. So if we were to connect each of these vertices, we see that we have a triangle. And if we were to identify the type of triangle we have here, is it concave or convex? Does it have any interior angles measuring greater than 180 degrees? Any reflex angles? No. Each of these look to be between 0 and 180 degrees, so it would be considered convex. And is it irregular or regular? Well, it doesn't look like all the sides are going to be congruent, and clearly all the angles are not congruent, right? This would be a 90-degree angle, and these two are not 90-degree angles. So we could say that this is going to be a convex irregular triangle. Now that we know that, we can find the perimeter of this given figure. So to find the perimeter, we need to figure out the length of each side. If your side lengths are horizontal or vertical, you're in luck. You can just count how many units that side length is. So this side length would be 1, 2, 3, 4, 5, 6, 7, 8 units long, meaning the measure of segment RS is 8 units. Over here, the length of this vertical side would be 1, 2, 3, 4, 5, 6 units. Therefore, the measure of segment RT is 6 units. This side length is where it gets tricky. Because it's not horizontal or vertical, we need to figure out the distance between these 2 points. How do we do that? The distance between 2 points we find by using the distance formula. So all we have to do is pick one of the points to be x sub 1, y sub 1, and one of the points to be x sub 2, y sub 2, and plug the coordinates into their corresponding spot in the distance formula. So x sub 2, that's -3, that goes in here. X sub 1 is 5, that goes in here. Y sub 2 is 3, that goes in here. And y sub 1 is -3, that goes in here. Now we just simplify according to order of operations. Inside our parentheses first, -3 minus 5, the same thing as -3 plus -5, so that's going to be -8. And then 3 minus -3 is the same thing as 3 plus +3, so that'd be 6. We then do our exponent, so -8 squared is going to be 64, and 6 squared is going to be 36. We then add these two together, 64 plus 36 gives you 100, and the square root of 100 is 10 units. So the measure of this given side is 10 units. So if I wanted to find the perimeter of this triangle now, I just add together the 3 side lengths, and I end up getting that the perimeter is 24 units.
Quit horsing around. Time for a U-try.
Okay, doing the same thing here. First, we want to graph the figure. So let's plot each point. Point A is at -9, 2. So we go over -9 on the x-axis, up 2 on the y-axis, put a point. Point B is at -3, 2. So we go over -3 on the x-axis, up 2 on the y-axis, put a point. Point C is at -3, 6. So we go over -3 on the x-axis, up 6 on the y-axis, put a point. And then point D is at -9, 6. So we go over -9 on the x-axis, up 6 on the y-axis, put a point. We then draw line segments connecting each of these points, and we see that our polygon here is actually going to be a quadrilateral because it has 4 sides. But let's get more specific. If we wanted to identify this figure, we got to identify it as concave or convex. So, does it have any interior angles that are greater than 180 degrees, or reflex angles where it's caved in? No, these are all pointed outward, therefore this is a convex polygon. And is it regular or irregular? Well, all of the angles look to be congruent, so it is equiangular. That's half of being regular. It also has to be equilateral. Do all the side lengths look congruent? Well, actually, these side lengths look longer than these side lengths, right? So, technically, this would not be a regular polygon. It would be an irregular polygon. It would be a convex, irregular quadrilateral. Now, rather than just guess what the side lengths are, let's go ahead and look at what the perimeter is. So in order to find the perimeter, we got to know the actual side lengths. And the good news here is that we have all horizontal and vertical side lengths, meaning we can just count. There's no distance formula involved. So if we want to find the length of segment AB, or the measure of segment AB, we just count 1, 2, 3, 4, 5, 6 units. So the measure of AB is 6 units. Then the measure of BC, we go up 1, 2, 3, 4 units. So we were right. These are not the same measure. So this is going to be 4 units. The measure of segment CD, 1, 2, 3, 4, 5, 6 units again. So we say that the measure of CD is 6 units. And then AD right here, or DA, is 1, 2, 3, 4 units. Therefore, we have all of the side lengths. So to find the perimeter, we just add those side lengths together, and we get that our perimeter of this convex irregular quadrilateral is 20 units.